Hello, everyone. Today we're going to talk about energy bar charts. And you will probably remember these discussed last year in physics as LOL diagrams. An LOL diagram looks like an L and an O and an L because on one side we've got a graph. On the other side, we've got a graph. They both look like L's, and then this circle here, which represents the system that we're dealing with. All right. Now, in this unit, we've been working with energy. We've been adding energy to things. In the lab, we added energy to water. We added energy to copper. And when we did that, we noticed a temperature change. And we noticed that the copper changed temperature much more than the water did. We found that it took a lot of energy to change the temperature of water, but it didn't take all that much energy to change the temperature of copper. All right, now I want to talk just a little bit about energy before we get into how to use these bar charts, okay? First, we need to know something about energy, and you've probably heard this before. Energy cannot be created or destroyed. And that sounds a heck of a lot like what we said before about matter, right? When we were working in Unit 1, we said that we said that matter cannot be created or destroyed in a chemical or a physical change. It goes even deeper than that in the fact that energy cannot be created or destroyed. And what energy can do is it can be transferred from one thing to another, and energy can also be stored. All right, and I know that you've learned some things about energy, storing energy and transferring energy when you were in physics last year. An LOL diagram is a way of seeing how energy is being transferred and how it's being stored in certain systems. Okay? I think the best way to really talk about energy is just to jump right into an example. And this is a very simple example. Here we've got a hot cup of coffee, and that hot cup of coffee is going to cool as it sits on a table. Okay? We've got three ways of storing energy here, okay? ETH is thermal energy, okay? So the energy of moving particles. I should write this down. All right, so ETH is thermal energy, okay? Energy stored thermally. Energy stored in the motion of particles. Okay, so particles are moving around and that motion is storing energy. That results in temperature. So temperature is the motion of particles, and thermal energy causes particles to move the way that they do. Okay, so when we're talking about ETH, we're really referring to temperature. Energy of phase, or phase energy, is EPH, okay? And this has to do with how particles are arranged, all right? I drew a little diagram here. These particles would be in the liquid phase, and then if we added heat energy to this liquid phase, you could imagine that we could form a gas, right? We could make the liquid evaporate into a gas. And separating these particles takes energy, okay? This is how we're storing energy in the form of a phase change, okay? So it takes energy to make a liquid into a gas because it takes energy to separate those particles. All right, now the other way that energy can be stored in a system is chemically, as far as we're concerned anyway. That's ECH, and I'm not even going to write anything about that. We're really not going to deal with ECH. That's got to do with chemical bonds. And there's nothing wrong with that. It's just that really doesn't have anything to do with what we're talking about in this unit. Okay, so we're only going to be dealing with ETH and EPH. All right, and this example will be a nice way to start, explaining what we're doing with LOL diagrams. Okay, so anyway, here we are. We've got an LOL diagram, and we've got hot coffee. Okay, I am going to draw an LOL diagram, a bar diagram, showing the temperature of the coffee being very high. Okay, so ETH is high. I'm going to use 2 bars to show a liquid. Okay, so the coffee is a liquid. Its phase is in the liquid phase. And we're going to use 2 bars to show liquid phase. Okay, in a few slides later, this will all be written down. Okay, now you can imagine that coffee cup is going to lose energy. Okay, so it's going to lose Q, right? It's going to lose energy. Heat is going to transfer out of the coffee cup. And when it does that, the coffee is going to become cooler. Okay, it's going to go to room temperature. And I'm just going to go ahead and draw ETH using only 2 bars. The phase has not changed, so I'm going to stick with 2 bars for the liquid phase. Okay, now you can see that we started with more thermal energy, and then we lost thermal energy. We lost thermal energy. Okay, energy cannot be created or destroyed, so I am going to draw 2 bars of energy being lost by the coffee cup. Okay, so if we count up all the bars on both sides, you'll see that we have not created or destroyed energy. 1, 2, 3, 4, 5, 6. Okay, we lose 2, so on the other side we've got 1, 2, 3, 4, 5, 6. Okay, we have not created or destroyed energy. We're just we've lost some energy, and that caused the temperature of the coffee to go down. So this is our first LOL diagram in our chemistry class. We're going to work on some more. Okay, so in this slide, they're just reiterating something that I already said. Okay, chemical energy is not involved, so we're just going to ignore chemical energy for now. Okay. In this slide, they're just establishing how we should represent different phases in our bar diagrams. So we'll try to stick to this way of doing it. Okay, we'll use 1 bar to form that to show that we've got a solid phase. We'll use 2 bars to show that we've got a liquid phase. We'll use 4 bars to show that we've got gases. Now, you might be wondering, why are we jumping to 4? It's because it takes a lot of energy to go from a liquid to gases. Okay, so really going from a solid to a liquid, it doesn't take all that much energy. So we're just going to add 1 bar when we're going from a solid to a liquid. Okay, going from a liquid to a gas takes a whole lot more energy. So that's going to involve 2 more bars. All right, so we'll stick to this representation in our phase diagrams. I'm sorry, in our LOL diagrams. Okay. All right. Now, in this slide, they're just showing us what we've already done, but you can see it. Since we did not change phase while that coffee cup was sitting there cooling, it just stayed liquid. It started as liquid coffee, and then it ended as liquid coffee. So we're starting with our phase energy is 2 bars. We're ending with phase energy as 2 bars. And in this slide, they're showing exactly the same thing that I showed you. It's showing us that in this cooling process, we're losing 2 bars of energy. So we're ending at an ETH that is only 2 bars where we started with 4. So that leads us to, all right, how are we going to represent different temperatures with these bars? Now, there's nothing, rigid about this, okay? We don't have to always do it exactly this way, but this is not a bad way to start. And maybe just, if we need to change in a certain situation or whatever, we can do that. But for now, let's just say that if it's really super cold, if it's below room temperature, okay, we're below room temperature, we'll use 1 bar to represent that thermal energy. At room temperature, like the temperature you and I are experiencing right now, that would be 2 bars of energy. Pretty warm, almost to the point where it's pretty hot to touch, 3 bars of energy. Boiling water, 4 bars of energy. Okay, we'll try to stick to this. But we don't have to be too crazy about it. This is not a quantitative kind of an exercise. This is more of a qualitative way of showing where is energy going, where is it being transferred, where is it being stored. Okay? All right, now in this final slide, they're showing you what I've already shown you. We're showing that heat is coming out of the coffee. Okay, that's Q, right? And we're showing that there are 2 bars of energy leaving the coffee cup, leaving us with only 2 thermal energy bars. All right. All right, now this one is going to be a little bit more tricky, okay, because here we are involving a phase change. And there is a good chance that we haven't had our class discussion yet about phase change, okay? We'll go forward with this anyway, and then when we come back together in class, we can talk about this. Okay, so in this case, we are starting with -8 degrees Celsius ice. Okay, and we're placing that ice on a counter, and it's going to become water at room temperature eventually. Now, this gets tricky because we are talking about a phase change. And we will talk in class about how phase changes. When we go through a phase change, we do have a change in energy, but we do not have a change in temperature. Okay? I'm going to draw a diagram for you to maybe help you to see this. All right. Now, in this example then, we're starting at -8 degrees Celsius. That is colder than the temperature at which water freezes. Okay? Now, this is going to not seem intuitive to you because you're going to think, oh, it's ice. It's going to melt. Yes, but not right away. Okay? So over time, we're going to add heat to that ice, and the ice is going to warm up from -8 degrees Celsius to 0 degrees Celsius. Okay? And now that it's at 0 degrees Celsius, as we add heat energy to this ice, now the ice melts. And as we're adding heat energy, notice that we are staying at 0 degrees Celsius. We have not increased temperature. All right? So let's really be clear here. All right? This is -8 degrees Celsius. We add energy to the ice, and the ice warms up to 0 degrees Celsius. When the ice reaches 0 degrees Celsius, it begins to melt. But the temperature does not change, and we're adding energy all this way until all the ice melts. Once all the ice melts, now we've got nothing but water, liquid water, and now the liquid water is going to warm up and warm up and warm up and warm up. Okay? There are 3 distinct areas here. We've got area 1, okay, where the ice is warming to 0. We've got area 2, where the ice is melting into liquid water. And we've got area 3, where the liquid water is warming up to warmer water. Okay? All right, so let's see what the next few slides tell us, okay? Okay, so let's take a look at this process. I redrew the graph that was on the previous slide, and really let's just talk about what's going on here. We're starting at minus 8 degrees Celsius, okay? That's below the melting point of ice, okay? So we're going to add energy to this ice, and the ice will not melt. The ice will not melt until the temperature increases to the melting point. The melting point for ice is 0 degrees Celsius. Okay, so everything that's happening in part 1 here, we're adding energy to just warm the ice up. We're going from minus 8 degrees Celsius to 0 degrees Celsius. Okay, that's hard for a lot of people to understand because you always think about ice. When you're warming up ice always melts, but it doesn't melt right away if it's not at the melting point. Okay, so again, we're starting at way below 0 degrees Celsius. So we're warming up the ice until we get to the melting point, and then the energy that we add to that ice goes into melting the ice. So now we're changing the phase, all right? I wrote a couple notes here. So in number 1, the part number 1, we've got all solid ice. In part 2, we are melting the solid ice into liquid water, okay? And notice that the temperature, very important here, guys, the temperature is not changing when that happens. We're adding heat all this time, and that heat energy is not increasing the temperature. It is only melting the ice. We're increasing in phase energy. Okay? We're going from solid to liquid until we get to the point where there is no more solid ice. It's all liquid at this point. Okay? Now that it's all liquid and we add energy to that liquid, it's going to warm up from 0 degrees Celsius to 20 degrees Celsius, which is our end point. Okay? So it's really important to understand what's going on here in that graph before we try to understand what's going on with our the LOL diagram. Okay? All right, so let's talk about what we've got here. The LOL diagram is partially filled in already. Okay, now here we're starting with a half a block of thermal energy, ETH. Okay, if we've got a full block, that usually means we're just merely very cold, right? But since we're very, very cold, we're going to only have a half a block there. There's nothing, there's nothing rigid about that. We're just doing this to show that there's a little bit of heat energy here, okay? We've got one block of phase energy because that represents a solid, okay? One block represents solid, and we established that a couple of slides ago. Okay, now what we're going to do, and we know that we're adding heat to this all the time. So heat is going into, it's going into the ice tray. Okay, so Q is going into the ice tray. When we get to the final here, when we're at the final stage, we're going to have liquid water. Liquid water is this bar. That's EPH, the energy of phase. That's 2 bars showing liquid. Here we were at solid. Now we've got 2 bars where we're liquid. okay? And that liquid water has warmed up, okay? So it's warmed up to about room temperature, and we're sticking to our, our semi-rule that 2 bars means room temperature. Okay, so what are we adding to this side to get to this side? We are adding, now watch my laser pointer, we're adding a half a block to get it to 0 degrees Celsius. And then we're adding another block on top of that to get to room temperature. Okay? So here we've added, and just watch my laser pointer. We started with half a block. We just added a half a block plus a full block. Okay? So I'm going to draw that in here now. In fact, I'm going to erase what I've got there, and I'm going to draw a half a block and a full block and another full block of Q going in, okay? So that is what we're adding, and maybe I should draw the segments there, okay? So this is what we just put into the block of ice, or the tray of ice, okay? And that's it. We not only melted ice, but we warmed up the ice, and then we took the melted ice and added energy to get it up to 20 degrees Celsius. So that is our LOL diagram, and that's where I'm going to leave it now, okay? Okay, just to look at this slide is showing exactly what I just showed you. And again, this slide is also showing you something that I showed you 2 slides ago. So this is basically the procedure that we're going to be following for using LOL diagrams to understand where energy is being transferred and where it's being stored in a system. All right, thank you.